Hello everyone. In this tutorial, we will cover lines in space. During last weeks, we talked about vectors and matrices. This week, I'm going to talk about lines in space, parametric equations for a line, symmetric equations, relationships between lines in space, and finally, distances in space, particularly the distance between a point and a line. So let's start with a brief talk about equations of lines. A direction vector of a straight line is a vector parallel to the line. According to the postulates of geometry, a point M0 and a direction vector Q determine the straight line, as you can see here. Let M be an arbitrary point on the line. The difference between the radius vectors of point M, which is R, and M0, which is vector R0, is a vector in the line that R minus R0 is parallel to the direction vector Q. And we know that two parallel vectors are proportional, so we can rewrite it in an equality. So this vector equality is called vector equation of the line. And arbitrary number t is said to be a parameter. Assume that we choose the Cartesian coordinate system. Vector r, r0 and q, we can represent it by their coordinates. So you can see their coordinates here. Then vector equation of the line can be written in the coordinate form as the system of three linear equations, as you can see here, where x, y, and z are running coordinates of a point on the line. Equation of a line in the coordinate form are called parametric equations of a line. So if we solve the parametric equations by eliminating t from these three equations, we obtain the canonical equations of a line, or non-parameter equations, as you can see here by this expression. If we have two given points, M0 and M1, on a line, then the vector joining these points serves as a direction vector of the line. So we can find the direction vector simply by subtracting these elements from each other. So if we know two points on a line, we can find the direction vector. Therefore, we get the following equations of a line passing through two given points. So just we simply substitute these variables into the canonical equations of a line, and we can find the following equations. So let's have an example here. Let be L a line passing through the points M1 and M2. So you can see the coordinates of these 2 points. We want to check whether the point A with these coordinates lies on the line or not. So in this case, we can use the formula canonical equation of a line for 2 points, for 2 given points. From the previous slides we had this equation. So we can substitute these coordinates to the x1 and x0 here, so we can get the equation of line L. The coordinates of a point A satisfy the equation, so which means that the point A is a point on the line L. Let's see another example. In this case, we want write down the canonical equations of the line passing through the point A with these coordinates and being parallel to the vector Q. In this case, again we can use the canonical equation form. So simply we can substitute the coordinates of point A to the x1, y1 and z1, and to the direction vector we have the coordinates here. So we can get this formula. Here there is a point that you should pay attention, that this is a symbolical notation. This one, y minus 3 divided by 0, is not arithmetic, so you cannot say that it is infinity. It means that the equation is y equals to 3. So this is a parallel to the line y equal to 3. Lines in a plane. On the xy plane, a line is described by the linear equation. As you can see here, ax plus by plus c equals to 0. If we have a point m0 on the line, so we can simply substitute this coordinate to the equation of the line. So we have ax0 plus by0 plus c equals to 0. Subtracting the second equation from the first equation, we obtain the equation of a line passing through the point m0. So we have a times by x minus x0 plus b times by y minus y0 equals to 0. The expression on the left hand side has a form of scalar product of vectors. So vectors n, a and b with the coordinates of a and b, and r minus r0. We know that this part is the difference between the radius vectors of point m and m0. So simply we can write it as a scalar product of two vectors, n and difference vectors of radius. You can see it here as well. So when the scalar product of two vectors are 0, it means that they are perpendicular to each other. Here there is one thing that you should pay attention, that the coefficients a and b can be interpreted geometrically as the coordinates of a vector in the xy plane being perpendicular to the line. So if a linear equation of a line is given and it is asked to find a vector which is a perpendicular to this line, so you can say that, easily pick this a and b, and you can say that this vector is a perpendicular to the line, because the scalar product of these two vectors yields to 0. The canonical equation of a line in xy plane has this form, where q, the qx and qy is the direction vector of the line. In the xy plane, an equation of a line passing through two given points m0 and m1 is written here. Sometimes it is helpful to express a straight line equation in a xy plane as this expression, x by a plus y over b equals to 1. You can see it here as illustrated. So in this case, y equal to 0 implies x equal to a, and if we insert x equal to 0 implies y equal to b. Therefore, quantities a and b are the x-intercept and y-intercept of the graph of the line. Equation, as it's shown here, is called equation of a line in the intercept form. A line on the xy plane may be also given by the equation in the slope intercept form, where b is the y-intercept and k is the slope of the line. If we have a point on the line m0, just we can simply substitute it in this slope-intercept form. Then the point slope equation of the line is y minus y0 equals to the k times by x minus x0. Let's look at this example. A line on the xy plane is given by the equation 2x minus 3y plus 24 is equal to 0. Find any 2 points on the line. In this case, simply we can substitute x to the 0, so we obtain y which is equal to the 8, and vice versa. So we can even put y equal to 0 to get x, or just choose any number for x or y. So the other one is that I choose x equal to 3, then y equals, we calculate it as 10. Therefore, 2 points we have 0 and 8, and 3 and 10 are the points which are on the line. The second one, the slope of the line. So we want to find the slope of this line. In this case, we can change it to the slope-intercept equation. So in this case, what we have to find out y. We can write it as y equals to the 2/3 of x plus 8. So from here we can say that the slope of the line is 2/3. The third one is that the x and y intercepts. So easily we can find them by looking at the slope-intercept equation. So from here we can say that the y-intercept is 8, and in order to find the x-intercept, we can set y equal to the 0, and we can calculate x from the equation that we have. So from this equation we found x equals to the minus 12. The other example here, we have in the xy plane, find the equation of a line passing through the point M1 with the coordinates of 5 and 3, and being perpendicular to the vector with the coordinates of 2 and -1. Here, as you remember, we can use the expression that I showed you before. So a times by the difference radius vectors plus b equals to the 0. We obtain. So simply here we have a, b, and we have x0 and y0. We substitute it in this equation, and we can find the equation of the line, which is y equals to the 2x minus 7. In this example, we have 2 points given on a line, and we want to check the following points A, B, and C are the points on the line or not. So first we have to find the equation of a line passing to 2 given points. So we have 2 given points. We can use the canonical equation form, and we got the equation of the line, and then simply we can substitute the coordinates of these given points into the equation and check are they consistent or not. Let's start with the point A. So by inserting -3 and 1 in the equation, we reach to this inequality. So the equation does not satisfy by these coordinates. So which means that point A is not a point on the line. For the case B, the point B, the same situation. If we insert the coordinates inside the equation here, it's not satisfied. So it means that B is not a point on the line. By inserting the coordinates of point C on the equation, we satisfy the condition, which means that point C is a point on the line. So in this section, we want to talk about angle between two lines. The angle between two lines is the angle between direction vectors of the lines. If we know the direction vectors of two lines, for example P and Q, then the cosine of the angle between line is given by the following formula. And as you remember, this is the scalar product of two vectors. So if you know the direction vectors of lines, simply you can use the dot product to find the angle between two lines. If two lines are perpendicular to each other, so which means that their direction vectors are also perpendicular. This means that the scalar product of the direction vectors is equal to 0. And if two lines are parallel, then their direction vectors are proportional to each other. So here in this expression, C is a number. And we can write it in the coordinate form as a proportional. So if two vectors are proportional to each other. So to find the angle between the lines, we need to find the direction vectors of lines. So let's consider some few particular cases. Let a line be given by 2 points, M1 and M2. So by this we can find the direction vectors of the line, right? And if a line in the xy plane is given by the equation ax plus by plus c equals to 0, we can easily find two vectors, 2 points on the line. For instance, just inserting x to the 0, we can find y, and if we setting y equal to the 0, we can calculate x. So we have 2 points on the line. So if two lines in the xy plane are given by equations a1x plus b1y plus c1 equals to the 0, and this one is for the second line, the angle between the line is equal to the angle between the perpendicular vectors n1, which is a coordinates a1 and b1, and n2, a2, b2. So we can use this formula. So if we have equations of two lines given in this case, note that perpendicular vector to a line is also called normal vector. So normal vectors n, so these are perpendicular vectors to the line. If a line in the xy plane is given by the equation as we remembered here, so then we have 2 points on the line. So easily just inserting x to the 0, we find b, y equals to the b, and setting y to the 0, we can find x. So in this case, we can say that the direction vector is a and minus b. If two lines in the xy plane are given by the equations in the slope intercept from y equals to the k1x plus b1 and y equal to the k2x plus b2, and theta is the angle between the lines, then we have a tangent of theta equals to the k2 minus k1 divided by 1 plus k1 times k2. If lines are parallel, it means that k2 equals to the k1. k2 equals to the k1 results to the 0, so tangent theta equals to 0, so they are parallel. And if the denominator became 0, so in this case we have a k1 times k2 should be equals to the minus 1. In this case the lines are perpendicular. Let's look at some examples. In this example we want to find the angle theta between the two lines. They are given by the following equations. So we have two equations of lines and we want to find the angle. So in this case we know the normal vectors to the lines. So for the first one we have a 3 and minus 4. For the second one we have a 2 and 1. So we can use the expression that we had before. So cosine of theta equals to the dot product and to the divided by the norm of vectors. So from here we can calculate cosine of theta, which leads to the 8 over 25 times by square root of 5. So from here we can say that theta is a our cosine, which means that theta is 45 degrees. This example, we want to find the theta, the angle between the two lines, if the equations are given in the slope-intercept form. So in this case, what we have? From the first one, we have the slope of the first line, which is a minus of square root of 3, and the slope of the second line is a square root of 3 over 3. And from here we see that k1 times k2 is minus 1, and if you remember from the tangent of theta equals to the k2 minus k1 divided by 1 plus k1 times k2. So from that equation we can conclude that these lines are orthogonal, which means that theta is equal to the 90 degrees. In this example, so we have three vertices of a triangle, and we want to find the equation of the altitude from the vertex A and write down the equation in the intercept form. So let's have a recall. What does mean altitude? In geometry, an altitude of a triangle is a line segment through a vertex and perpendicular to a line containing the base, the side opposite. So here, for example, this vertex, so this is a line segment to the opposite line containing the base. So we want to find the equation of the altitude from vertex A. In this case, assume that we have a D with the coordinate of x and y. Y is an arbitrary point on the altitude form from the vertex A. Then the vectors AD, so we have x minus 2 and y plus 1, so y plus 1, and BC, so BC is like a 9 minus 4, 7 minus 4, we have a 5 and 3, are orthogonal, right? Yeah. So therefore the scalar product of AD and BC is equal to 0. So let's write the scalar product of two vectors, AD dot BC. So it leads to this one equals to the 0 because they are perpendicular to each other. From here we can write it the equation of the line, but we want it in the intercept form. So we can just do some mathematical operations here and we can find the intercept form of the line. The last part, we have a distance from a point to a line. Consider we are in a xy plane and let n be a normal vector to the line and m be any point on the line. So m is any point on the line and n is the normal vector. The distance d from a point P, which is not on the line, is equal to the absolute value of the projection of Pm, absolute value of projection of Pm on the vector n. So the absolute value of projection of Pm, vector Pm on n, as you remember from the second tutorial, we have a dot product of Pm and n divided by the norm of vector n. In particular, if the line is given by the equation ax plus by plus c equals to 0, and the coordinates of the point P are given by, not given, are x1 and y1, so we can say that the normal vector is vector n with the coordinates a and b, and the vector Pm, so we have a x1 minus x0 and y1 minus y0. So from here we can find the distance from the point P to the line and calculate it by this formula. So this one is the dot product of Pm and n, and this one is the norm of vector n. Since m with the coordinate of x0 and y0 is a point on the line, so we can substitute them here. So we got ax0 plus by0 plus c equal to 0. Therefore we can say that, and this one is equal to 0. So from this equation we can say that ax0 by0 plus c is a 0. So we can add this one c here. So we change this equation to this expression. Okay, let's continue with the relative positions of lines. Let two lines L1 and L2 be given by their equations. For example, here we have a canonical form, and we know the direction vectors according to the from the canonical form we have it. In order to determine the relative position of the lines, it is necessary to consider the equations of both lines as a system of linear equations. Each line is described by two linear equations, and so we have the following system of four linear equations with three unknowns x, y, and z. So we can say that this part is one equation and x and z is a second equation. For the second line, the same story. So we have an x part and y part and x part and z part. So we have four equations with the three unknowns. Let's look at on some possible cases. Assume that the system is inconsistent. So do remember about consistency and inconsistency. 2 weeks ago we talked about it. Inconsistency, if the system does not have any solution. So in this case, the lines are either parallel or skew. If the coordinates of the direction vectors P and Q are proportional, so these expressions satisfy, then the lines are parallel. Otherwise, they are skew. Suppose that the system is consistent and the rank of a coefficient matrix equals to 3. So we have a consistent solution and the rank is a full rank, so 3. Then L1 and L2 are intersecting lines. they have exactly one point of intersection because they are consistent. If system is consistent and the rank of the coefficient matrix equals to the 2, so it's not a full rank matrix, then the line coincide with each other. Let's look at the example here. For the pair of lines, determine whether the lines are equal, parallel, but not equal, skew, or intersecting. So we have two lines and equations related to them. So for the first line, we have a direction vector 2, 1, and 1. And for the second one, we have 1, 3, and 5, and minus 2, sorry. So they are not parallel. Why? Because they are not proportional of each other. So it means that either intersecting or skew. So let's determine whether the lines intersect. So in this case, we see if there is a point XYZ that lies on both lines. To find this, we use the parametric equations to create a system of equalities. So here we say that so x, they should be the same, y they should be the same, and z should be the same. So we have a 2s minus 1 equals to the 3 t minus 3. And for the y and z, the same story. From the first one, we can say that the t equals to the 2s plus 2. So we calculate t from here. And we substitute it into the second one. From here, we substitute it here. So t substitute here. We got s. We calculated s. So we have a s equals to the minus 3. Now, let's substitute it into the third equation. So yields in a contradiction. So from here, we have a s equal to the 1. Which means that there is no single point that satisfies the parametric equations for line L1 and L2. So which means that they are not intersecting. And the coordinate of the direction vectors are not proportional. We know it from here. So which means that they are skew. So you can see it here. So they are not parallel and they are not intersecting. So the last example here, we have a pair of lines and we want to determine that they are equal, parallel, but not equal, skew, or intersecting. In this case, what we have, so from here we can say that the direction vectors of the first one is 6, minus 2, and 3. And from the second one, we have a 6, minus 2, and 3. So they are equivalent. So they have a same direction vectors. So in this case, direction vectors are proportional to each other. So we can say that these two lines are parallel. So next week, we will talk about planes in space, and we will cover general equation of a plane, equation of plane passing through 3 points, other forms of equations of plane, angle between two planes, distance from a point to a plane, and relative positions of planes, and relative position of a plane and a line. So thank you, and see you in a question and answer section.